Whenever you're ready to go, you're ready to go.
I
Yeah,
think he's
I'm
eagerly
totally ready.
waiting to go.
Okay, you go ahead. And yeah, and start sharing your screen. Yeah, great. All right, fantastic.
Yeah. Can you see my presentation, liquid crystal self-assembly, the slide?
Yes.
Okay. And can you hear me clearly, or I can change microphones if not?
No, I can hear you. You could be a little bit louder, so just sort of maybe, you
Okay,
know,
I'll just speak loudly. Perfect.
yeah.
Okay. Right. Right. Thank you, Dr. Shahid and Dr. Atta, for organizing this workshop, and also to Dr. Sriram for such an excellent talk before me. Some of the things that I'll point towards the end of the talk, I think he's explained very well, and these are things that I've just started doing. So I think I've a lot to learn from him. So the title of my talk is Liquid Crystal Self-Assembly. Uh, I will spend quite a lot of time introducing the attendees to different liquid crystalline phases. We will then, after we introduce pneumatics, semectics, and discotics, we'll go on towards looking at self-assembly of supramolecular fibers in discotic liquid crystals and what factors affect the fibers. Uh, I've recently become interested in actin filaments, so I'll link those fibers to actin, and then we'll go towards topological defects in nematic crystals. So to start off, then when we speak of molecular self-assembly, well, then the term molecular self-assembly basically implies the spontaneous formation of these supramolecular structures, right? And these are typically driven by local interactions, especially between molecules, if we're talking about molecular self-assembly. Liquid crystals are basically their mesophases, and they have properties that are intermediate between those of solid crystals and isotropic liquids. Um, Before I started this field, I used to think that liquid crystals are basically just found in smartphone displays. But as I got to know more and more as a student, I realized that essentially they're everywhere. I mean, you can look at the phospholipid bilayer in a cell membrane, and that's an example of a liquid crystal. But the physics that drives liquid crystallinity is basically everywhere. Um, they have varying amounts of orientation and translational order, and that's how you characterize them either as a nematic, a semectic, a cholesteric, or a blue phase, or whatever. And a liquid crystalline phase can form as a function of either temperature. If that happens, we call it thermotropic. And a lot of the liquid crystals you typically use in displays are thermotropic liquid crystals. A lot of biologically relevant liquid crystalline processes and structures are what are called lyotropic liquid crystals. And that's where nature harnesses the different polarities of a molecule, and different polarities lead to uh, large scale ordering such that you can form micelles and so on and so forth. So just to compare then, a liquid crystalline can have a varying amount of positional order, and almost always they have some orientational order. An isotropic liquid would have neither of those. A plastic crystal would allow some positional order of whatever constituents it has, but no orientational order, and a solid crystal would have both. On the right here, you have an example of a thermotropic liquid crystal, uh, those liquid crystals that form as a function of temperature. And you can see that if you heat such a liquid crystal and you look at it under cross polarizers, I'll explain why cross polarizers in the next slide. But the idea is that they're birefringent, so we can see, so when they're in the mesophase, you can see something under cross polarizers. And as you heat them out of the mesophase, you get an optically isotropic dark state, right? So that's a typical transition you would see under a microscope for a thermotropic pneumatic liquid crystal. Now, speaking of pneumatics, pneumatics are the most simple and the most disordered kind of liquid crystals. A typical rod-shaped. This is how a physicist looks at a pneumatic. This is how a chemist looks at a pneumatic. Um, so a typical pneumatic liquid crystal possesses orientational order. There's almost always some shape anisotropy. They can be disc-like, but a lot of common pneumatics are these rod-shaped calamitic molecules. Um, the molecules tend to be a lot of molecules tend to be polar. I mean, polar in the sense that they have a net permanent dipole, but you almost always have some level of dielectric anisotropy because of the anisotropic shape and the functional groups. And this at optical frequencies, this also translates to optical birefringence, which is what all liquid crystal displays tend to harness. And when we talk of optical birefringence, the idea basically is that if you have, for example, such an nematic liquid crystalline phase where the rods on average point in the same direction, they are in constant motion, but on average their directors point in some along some direction. Um, then that average is defined by this unit vector n hat, which is the molecular director. And the idea is that if you have light polarized along the director, then it encounters a certain refractive index Ne, and if it's polarized perpendicular to the director, it sees this ordinary refractive index N naught. This, of course, is a uniaxial crystal, nematic crystal. And in the case of nematics, well, we can specify the degree of order in a mesophase by this order parameter. And so for a nematic liquid crystal, you can typically have this theta would be the angle between, on average, between the detector and the molecules. So S equals 0 would imply an isotropic phase. S equals 1 would imply a fully aligned nematic phase. And for most materials, S is between 0 and 1. Right. So in terms of understanding the thermodynamics of these systems, there are many models out there. The simplest model that explains the orientation or the energy of non-chiral liquid crystals is the Frank or the Frank-Austen elastic energy model, where essentially you have these rod-shaped molecules, and these molecules have these continuous deformations. Um, so in general, you can break those deformations down into three types. You can have splay deformations, you can have twist deformations, or you can have bend deformations. And there's an energy cost associated with every deformation, right? And so these are elastic constants, just like if you stretch a spring, you have k delta x square, 1/2 k delta x square. Similarly, you have an elastic energy associated with a splay deformation, a twist, and a bend. And fundamentally, the magnitude of these elastic constants depends on the chemistry of the molecules, the functional groups, the intermolecular forces, the viscosity, so on and so forth. Right. So this is electrostatic in nature, but this allows us to model them. One limitation of this of the Frank elastic energy model is that it does not allow us to cater for discontinuities, which we will talk about later on, and for that you need the Landau degen or the Q tensor framework. So talking about other liquid crystalline phases, so you can have symmetric liquid crystalline phases where, in addition to orientational order, you also have positional order in one dimension. So along one dimension, the center of mass, you'll have some periodic variation in the center of mass. These molecules tend to have stronger intermolecular forces, so or you can have longer molecules than you would have in a nematic liquid crystal. And those stronger intermolecular forces can sometimes give you these more ordered phases. And a symmetric phase will typically give you a focal conic texture because these molecules tend to form layers, and these layers tend to form these cones, and where these cones meet, you get these defect lines. So this is the typical texture of a focal conic symmetric liquid crystal. Similarly, you can have chiral liquid crystals. These are fascinating materials. So basically, if you take for example, in the simplest case, if you take a nematic liquid crystal and you add to it a chiral molecule or a chiral dopant, what you get is that your directors, I mean, it's still a nematic locally, but on average, your directors start to twist, and you get this characteristic length, which is called the pitch. And these twisting directors, and because of the fact that your material was optically birefringent to start off with, you can form photonic band gaps, and you can form 1D photonic band gaps such as these. And more recently, you can actually form 3-dimensional photonic crystals and photonic band gaps, and which are called blue phases because they used to look blue, but they're not actually blue. And so these are fascinating materials also, and they can be used to form lasers, thermometers, so on and so forth. The final type of liquid crystals that I want to introduce are disc-like liquid crystals or discotic liquid crystals. Now, discotic liquid crystals are typically formed rather than rod-shaped. The molecules are disc-shaped, and the typical discotic liquid crystal would have some rigidity at its center or a rigid core, and then it would have flexibility or fluidity via alkyl chains in the periphery. So this would be a prototypical discotic liquid crystal. It's also called hexaalkyl oxytriphenyline or HAT6. Now, discotic liquid crystals can also form nematic phases. In fact, a lot of these high-end displays that you buy have a thin layer of discotic nematic to increase the viewing angle. But typically, discotic liquid crystals form columnar mesophases. And what a columnar mesophase basically is that you have, if I take you here, so what you would have these disc-shaped molecules, and the molecules would be stacking on top of each other via pi-pi interactions or uh, or induced dipole interactions. And these columns would then stack into two-dimensional lattices, a hexagonal lattice, a square lattice, or a rectangular lattice. And so you have a highly anisotropic structure where you have like these polyaromatic cores stacking along the molecular columns. And if you go in this direction, then you have this alkyl chain core. So it's a highly anisotropic structure. And I actually got interested in discotic liquid crystals because I wanted to make efficient solar cells. And I was interested in using these materials as organic semiconductors. That's another story for another time. But just to point out, so these are optical micrographs of a columnar mesophase. So this molecule that I showed you, HAT6. So if you look at the DSC, then what we get is that under heating from room temperature, you have a crystalline phase. Then you have after about 64 degrees Celsius, you have a columnar mesophase, and then you have isotropic after 100, right? And this is what you would see under an optical microscope. There are two main types of alignment of a columnar phase. It could either align face on a substrate and form these standing columns, or they can basically lie down, and the director would be, or the axis of the columns would be parallel to the substrate. Typical intercolumnar spacing between these stacks of molecules is about 2 nanometers, and of course this depends on the size of the molecules. And typical spacing between the molecules is about 4 angstroms. Now, I mentioned that I was interested in these to make solar cells, and at the time I was doing quite a lot of molecular doping. So it just so happened that I read a few papers of people who were doing iodine doping of these to increase their conductivity, and so I just added some iodine in acetonitrile to these one day, and we realized that they actually form gels. And this thing formed, and I wasn't interested in it for a few months, but then I came back to it eventually to just explore it a bit more. And that's when I actually started getting interested in self-assembly and soft matter. So basically what we found was that if you take this molecule, which is a columnar discotyl liquid crystal, and you add a bit of it in a solvent such as acetonitrile or ethanol or methanol or isopropanol, the OH group is important actually, because the hydrogen bonding is actually very important. You get so you mix it and you cool it down, and from a clear isotropic liquid you get a murky gel formation. And under microscope, what you have these micron scale fibers, which are birefringent because the molecules which made those fibers are birefringent. Um, and, and what they form is a physical gel, because you see these columns were never covalently bonded in the first place. And so now what you have is that you have these pi stacked columns interacting with the solvent and leading to the formation of a three-dimensional stable network in which the solvent is free to slosh around, and these fibers are basically holding it all together. So that's basically a physical gel. And we got more and more curious as to understanding the nature of like, for example, how are the molecules arranged in these fibers? Are they crystalline? Are they liquid crystalline? So on and so forth. And one thing that was really fascinating me for a while is that when I used to put them, put a cell of these under a microscope, we used to see this wave guiding effect, and we used to see these alternating bright dark brushes, uh, which I initially thought is probably some sort of chirality in these. But then we explored them a bit more, and I'll talk about them. So basically, we got physical gel formation in the Scotty liquid crystals, and so the first question that I wanted to ask was that if you know you have this polyaromatic core and then you have these alkyl chains on the end. If I change the length of these alkyl chains, what happens to these fibers which form the network which then stabilizes this gel? So what we first found was that the shorter the alkyl chains, the the thicker your fiber aggregates. So for example, you have a C4H9 chain viscosity liquid crystal over here, and you have a C7H15 viscosity liquid crystal over here. This is in dark field, this is in bright field. Uh, and so the fibers get thinner and thinner as we increase the alkyl chain length. Now, in terms of DSC, as you increase the alkyl chain length of this viscosity liquid crystal of the pure material, what you see is that you add more and more fluidity with the same amount of rigidity, and so you lower the liquid crystal to isotropic temperature. So for example, for HAT7, this pink transition here at about 90 degrees Celsius is your columnar to isotropic phase transition temperature. But for HAT4, that's all the way at 145. But interestingly, in the gels, we saw the opposite trend, where the longer alkyl chains had a higher gel to isotropic transition temperature, uh, probably because of the stabilizing effect of the interaction of the longer alkyl chains with the solvent. Now, the next thing that we wanted to explore was that okay, you have these disc-like liquid crystalline molecules, and they're forming gels in these solvents. What if we change the concentration? So I took this HAT7, so this triphenyline core with C7H15 attached to it, and varied the concentration from 5.36 millimolar to 1.31 millimolar in acetonitrile. And what we saw was that lowering the concentration leads to longer and thinner aggregates, um, and which had a lower clearing temperature, but the fibers were definitely longer. And perhaps we hypothesize that this is perhaps because you have fewer nucleation sites when you have a lower concentration, um, and this was also it's had effects on the clearing temperatures also. Now, I mentioned the first thing that was bothering me or really making me curious was these alternating bright dark fringes that we were seeing under cross polarizers with these molecules. So when we put them under an SEM, we saw something very interesting. So under SEM, what you see is that you have these fibrils that have a diameter of about 480 or 450 nanometers, some even thinner than that, such as this one. And these fibrils were bundling together to give us these birefringent fibers that we were seeing under an optical microscope. So each of these fibers that we were seeing under an optical microscope, which had a thickness of about 3 microns, was actually made up of many fibrils of about half a micron. And these fibrils were basically intertwined, and in some cases they were essentially merging into each other and branching out, so on and so forth, as you can see here. So and they did not look cylindrical, which was what we initially thought that they looked like. So to our best guess, these molecules are forming these kind of aggregates in a solvent medium, and so basically you have these you have this elliptical cross section, and so what we think is happening is that you have these elliptical fibrils coalescing into these large fiber bundles, which also have some sort of elliptical cross section, and this tends to occasionally rotate, and it gives you different amount of scattering which gives you these fringes that you see here. Now, the really nice thing about this system, and which is why I got really interested in it, is the reversibility. So, you heat these gels to about 45 or 50 degrees Celsius in a vial, and you get a complete isotropic medium. For example, a battery or a solar cell application, that's excellent because you can fill it into your device, cool it down, and you have in situ gel formation, right, at quite a low temperature. And this is reversible any number of times. Coming back, so the next question we wanted to answer was that how are the molecules, how are these distorted liquid crystalline molecules oriented at the surface of these supermolecular fibers? And to study that, what we did was we actually made these quite interesting cells where you had these. So these are sandwich cells where you have these fibers, which are the black dotted lines here, and we filled these cells with a nematic liquid crystal, nematic liquid crystal 5CB, 5-cyanobiphenyl, and we tried to figure out what the alignment of the 5CB is with these on top of these fibers. The idea was that because these molecules have these alkyl chains, the nematic liquid crystal would either align homeotropically or along the alkyl chains, or it would align face on in a planar direction. Um, to, to the best of our understanding so far, there is some sort of hybrid alignment of molecules at the surface of these fibers. So it's neither just alkyl chains, neither just face on basically polyaromatic cores. It's somewhere in the middle. So I said that after working with these systems, and of course we were focusing on photovoltaic applications initially, and then we started getting more curious about what drives what makes these fibers form, how are how are the molecules oriented within them, how can we play around with their morphology by tuning concentration and tuning the molecular size. Then Dr. Shahid actually got me interested in very similar looking fibers in actin microfilaments. So of course the fibers of distorted liquid crystals form as a function of temperature. So you probably get some nucleation, and then you have more and more molecules coalescing on whatever thing is nucleated, and then the fibers basically grow from there. And it's the interaction between the solvent, favorable and unfavorable interactions, and favorable interactions between the intermolecular interactions, and basically that drives elongation of these fibers, which are stable at a certain temperature range. Now, actin, I'm not an expert in actin microfilaments, so I could get this wrong. But I still think it's a fascinating system. So I want to draw some parallels here and explore this further. So the molecular columns I spoke about have a column-to-column spacing of about 2 nanometers. And if you make a gel out of them in a solvent, then you get fibers of about 450 nanometers. Now, actin filaments are made up of globular actin monomers that are hydrolyzed into these long actin filaments. The width of these filaments is about 7 nanometers, so that's comparable to the column-to-column spacing in these distorted liquid crystals, and they are sort of comparable in terms of length also. I think I've actually so this needs to be here. This needs so for them in terms of length, you can have distorted liquid crystal fibers between 10 microns to a millimeter, as we saw here. So for example, the scale by here is 200 microns, and look at the length of some of these fibers. So these fibers tend to last on the order of a millimeter, and actin microfilaments can go from 30 nanometers to 200 nanometers, 100 microns. I'm sorry, these columns, just for this one, these columns will be swapped. In terms of persistence length, which is basically a measure of the rigidity, or how long the local tangent takes to become sort of irrelevant, the persistence length is also somewhat comparable. It's about 10 to 30 microns in actin filaments. It's about 1 micron to 1 millimeter in these distorted crystal fibers. Actin filaments tend to bundle by cross-linking proteins. They tend to form these networks, which are really important in cells and the cytoskeleton. Similarly, discontinuous crystalline fibers tend to branch out and coalesce and make these three-dimensional networks that can hold a solvent together and form a physical gel. Discontinuous liquid crystalline fibers are molecular in nature. In analogy, actin filaments are molecular in nature. Actin filaments are formed by two strands of globular actin. These are formed by these columns of molecules, which which then aggregate to form these. And the molecule size are also similar. This is also swapped. So the molecule size in a discotic crystal is about 1 nanometer. The molecule size of actin is about 5 nanometers. I apologize. These two columns should be swapped, and these two should be swapped. So the question that I want to actually explore now is that, given the tools that we've been using to look at these discotic crystalline filaments, for example, their interaction with nematics, can we do something similar with actin microfilaments? And that's something that we want to explore in coming months. Now, the next essentially topic that I want to talk about is topological defects in liquid crystals. And this is also recent work that we've started in our group. And this is the motivation for this is linked to what Dr. Sriram presented right before my talk. So a topological defect is essentially it's a discontinuity that you can't remove via a smooth transition, right? For example, if you have a donut, then if you have a path around, in if you have a path that encloses that hole, so essentially you have a topological defect there, right? So similarly speaking, in nematic liquid crystals and in ordered matter, you have these topological defects. And so over here, we have a typical nematic liquid crystal viewed under cross polarizers. And what you typically see, this is called the Schlieren texture. And what you typically see is that you get these brushes. So you either get these 4-point brushes or you get these 2-point brushes. And if you look at a 4-point brush, what that basically corresponds to is basically a full rotation of the molecular director. Molecular director meaning a full rotation of the long axis of the molecules, right? So if you go around these 4-point brushes once, you traverse the molecular director. The molecular director sweeps out 360 degrees or 2 pi. If you go around this kind of a defect once, the molecular director sweeps out 180. So these are topological defects in a nematic liquid crystal. You have topological defects in nematics, in symmetrics, in cholesterics, in different types. I'll just focus on nematics for now. These defects have an associated binding number, which I talked about, and they also have a charge. And this charge basically has to do, the way to characterize charge, the way we do it is that we rotate our samples under cross polarizers. And if you have a positive charge, then these brushes rotate in the same sense as the rotation that you perform. And if you have the opposite charge, they rotate in the opposite sense, right? And so that's basic. So why are we interested then in topological defects in liquid crystals? The reason I got interested is because I spoke of defect lines in symmetric liquid crystals. And similarly, you can have topological defects of integer of +1, -1 charge in nematic liquid crystals. Now, it turns out that these defects are sites that in some sense give order to particles that are dispersed within these nematics. So for example, if you disperse colloidal particles or quantum dots in this medium, they tend to organize along these discrimination lines or topological defects. And one of the most fascinating things that I actually came across a couple of years ago, I think 1 year ago, and we've started exploring this now, is that if you so it's this paper here, Command of Active Matter Topological Defects by Professor Oleg. So basically, if you disperse bacteria, and this is a +1 defect. If you go around it, the director rotates by 360. If you disperse bacteria in in a nematic liquid crystal with these topological defects, then they tend to aggregate around positive defects, and they tend to like aggregate away from negative defects. And you can see that, and not just that, like the bacteria, they follow these directed profiles. At least that's my understanding of it right now. And this is not, and these are the hydrodynamic or elastic interactions that Dr. Sriram explained so nicely in the talk before. But so the idea is that if you can control these topological defects, if you can control where they happen and when they happen, you can guide active matter such as bacteria or even microtubules or microfilaments, which is what we might start off with. Um, and then you can of course make applications for these in biosensing, so on and so forth. So what we're doing in the lab now is that we're making two-dimensional arrays. We're following the study, so this has been demonstrated before. Uh, we're doing it slightly differently. So we're making two-dimensional arrays of on silicon. So this is a square array. These are holes which extend all the way down to the substrate, and this is made by SU8, which is a negative photoresist on a silicon substrate. And the idea is that we're making square arrays, we're making hexagonal arrays, we're making tetragonal, rectangular, all kind of, all the 2D Bravais lattices, and we want to basically create deterministic topological defects of integer charge, and then disperse either microtubules or microfilaments and active matter in it, and see how we can basically control their motion and aggregation. So these are the sort of devices that we're making. So we take two substrates. We take a silicon substrate. We pattern it such as this. This is this is 100 micron scale bar. So these are 20 micron patterns. And we coat. We functionalize the surface with a surfactant such that it induces a homeotropic or vertical alignment of liquid crystals once the cell is filled with it. On the top substrate, it's kept transparent. It's a glass substrate. We deposit a planar alignment layer, and then we fill it with the liquid crystal. And our initial results are something like this. So these are our initial results with a nematic liquid crystal. They agree with what's already published in literature, which is that what you get here is that wherever you have these holes, you have air pockets form when you capillary fill them, and wherever you have this resist, you have your nematic, and the sort of, because you see the boundary or the surface
Ammar,
is
you have 5 more minutes.
okay. I'll finish by this. So the surface is basically forcing this alignment, and you get this you get these 4-point brushes here between these air gaps that we patterned, and effectively you have defects on the air gaps also. And between these air gaps, we see -1 defects, which means that I mean, if you were to rotate the sample, the brushes would rotate in the opposite sense. And so with nematics, we're able to realize these ordered arrays of topological defects. We've also made these with symmetric liquid crystals, and we've seen these kind of structures here. I don't think we have topological charge here. I need to reconfirm this, but my current understanding is that we don't have topological charge here, but we do have stable and reproducible topological charge and pattern substrates in the case of nematic liquid crystals. The next thing we want to do is that we want to make electrically switchable topological defects. And then by basically replacing these substrates with conductive, transparent conductive electrodes, and basically then you can, for example, the idea would be you have, let's say, bacteria or microtubules or filaments in a certain place. You apply a field, the boundary conditions are gone, and then you can remove the field and the boundary conditions are back. So you can do all sorts of interesting physics with that. And then the second thing we want to do is that we want to induce these defects in aqueous nematics. We've been doing this in these hydrocarbon 5CB, 8CB nematics, but we want to do it in aqueous nematics also. That basically summarizes everything I wanted to say. So we've talked about self-assembly of discordant liquid crystals into these supramolecular fibers, which is non-covalent, and they're stabilized by hydrogen bonding with the solvent and amongst each other. And then we've talked about topological defects, why we're interested in them, and the sort of devices that we're making. Thank you. Oh yeah, and I'd like to thank my PhD student Kurtinain, MS student Sarish Iqbal, and BS student Mariam Kaisar, who they've basically done almost all of this work, and other members of my group and the HEC of Pakistan. Thank you, and I would be glad to take any questions.
Great. Okay, Ammar. So we can take two questions and then we need to move on to Sabi's talk because, I mean, we've got, just because, yeah, so we're not going to have a break. Maybe a couple of questions.
So can I ask a quick one?
Yes.
So, Ammar, it was a very nice talk. On this, those fibrils that you had that sort of periodic bright dark pattern. What determines it looked very regular. Is there an understanding? It looked kind of like there's a quite well-defined preferred wavelength. So I didn't understand if you gave an explanation of exactly why there was a preferred
That's
wavelength.
what I also thought initially. I thought that this is a very regular pattern, and I spent quite a lot of time actually looking at them a lot more carefully. It turns out they're not that regular. So they look regular in this case, but you can have like in the same sample, you have different regions exhibiting different length scales. Even here, for example, you can see that they're closer in some fibers and further away in others. And I actually thought that this is because of some sort of twisting of maybe you have some chirality, unintentional chirality in the system or something else. But the best explanation that I could give is that we have these fibrils, and these fibrils are forming these large bundles, and these bundles are twisting every now and then, and it's the twist of those bundles that's giving us these scattering.
I see. So this is published work, right? These things. So I can read about this somewhere.
Yeah.
Okay, so I will.
This is published in this paper. Yeah.
Okay, all right. Okay, I'll talk to you more later. It's very interesting. Thanks.
Yeah, no. I also have, I'm curious about the periodicity. So I guess if you don't get any peaks. If you do a spatial frequency, one-dimensional spatial frequency thing, you don't get peaks from some of these images, I guess. You must have done that. So yeah, it's interesting.
Yeah, we should do that.
Because at least, the couple of examples, I thought there was some, mean periodicity there, but maybe not. I mean, so yeah. Okay, any other questions? Okay, so then we should go on to, is Sabi around?